Okay, last section of chapter 7, and then we're on to chapter 8, and that's the last chapter of new materials. So we're really coming close to the end of things. So I have another set of prepared notes for this section because, again, there's just a lot of writing otherwise. Anyway, so in 7.4, we talked about vectors from a geometric perspective. And now we're going to talk about vectors again from an algebraic perspective. And it's a lot, well, in certain ways, it's a lot easier to work with vectors algebraically than it is to work with them geometrically. The way that we think about vectors algebraically is we take vectors, and remember from our discussion in 7.4 that vectors can be kind of moved around wherever you like, as long as their magnitudes and directions aren't changed. They still represent the same quantity. And so in particular, we can take a vector and we can place its initial point at the origin of a coordinate system. And then vectors that are placed in the coordinate system that way are called position vectors. And when they're placed that way, since all of the vectors are going to have their initial point at the origin, that means that they can all be uniquely described just by looking at the coordinates of their terminal point, right? So if vector u is a position vector with a terminal point at the point AB, then we write vector u equals AB, but we use these angled brackets. And I don't know if you can see that. I'll zoom in on this. So you can see kind of the difference, but here I'm using rounded parentheses and here I'm using angled brackets. Might help if it were more focused. Oh, that's not any better. I can't control the focus on this. It only has like an automatic focus feature, and it's really kind of, I wonder if I change that setting, if that's any better. No, still not. Yeah, so it only does an autofocus thing, and it doesn't focus very well in my opinion. But anyway, so we're using these angled brackets there. A is called the horizontal component, B is called the vertical component. And then you may, when we talked about angles, like at the very beginning of the semester, we talked about angles in standard position, and we basically described them the same way, right? So, so consequently, like when we talk about the direction angle of a vector, we're talking about the positive angle that the vector makes with the positive x-axis. So with those kind of definitions in mind, here's how we can think about magnitude, direction angles, horizontal, vertical components, and so forth, right? So the magnitude of vector u is going to be the square root of a squared plus b squared, right? Where u is ab, right? So it's the square root of a squared plus b squared. The direction angle satisfies tangent theta equals b over a. Of course, a can't be 0 in that case. The horizontal component is magnitude of u times cosine theta. Vertical component is magnitude of u times sine theta. And I'm not going to prove each one of these things. It should be fairly clear. Oh, that's what that setting does. It just automatically zooms now all the time. I'm going to turn that back off. Bear with me through my technical difficulties here, but anyway, I'm not going to prove each one of these things. I'm just going to draw a picture, and the picture should make most of these things pretty clear. So let's say we have a vector, and this will work for any vector that's in any quadrant that's pointing in any direction, but I'm just going to, for the sake of ease, display the vector here in quadrant 1. And so let's say that this is vector u. And vector u we said was going to be AB, right? So we'll say that that this terminal point out here is AB. Okay, now you can obviously make a little right triangle out of all this. And this right triangle would have one of the legs would be A, the other leg would be B, right? And the magnitude, or the magnitude of vector u is the same thing as the length of this vector. So really, like the length of that side is just the magnitude of u. Anyway, so here you get like this first statement, right? This is just Pythagorean theorem. A squared plus b squared equals magnitude of u squared. So you take the square root of that and you get magnitude of u is square root of a squared plus b squared, right? This angle here is the direction angle theta. So again, you see that tangent theta has to be b over a, just by definition of tangent, right? So that takes care of the second one. The horizontal component. So if we're thinking about u here, if we're trying to describe what a is in terms of like theta and the magnitude of u, well, we could say cosine theta is a over magnitude of u, right? So maybe I'll write that down. Cosine theta is a over magnitude of u. If we solve for a, then we see that a is magnitude of u times cosine theta. Right, and that takes care of that one. And then a similar argument could be made for the vertical component, right? We could say, well, sine theta is b over magnitude of u. You solve for b and you get, b equals magnitude of u times sine theta. So, so those are all those facts. And pretty much looking at a picture, you kind of get all of them for free, more or less. But let's work out a couple examples. This first one says, find the magnitude and direction angle for the following vectors. And this first one is just the vector 3, 1. So the magnitude, we said, is going to be square root of a squared plus b squared, right? So the magnitude of u is the square root of a squared plus b squared. So that's the square root of 9 plus 1, which is root 10. Okay, so there's the magnitude. The direction angle, it says, satisfies tangent theta equals b over a. So we could say tangent theta equals 1/3. Now, you might think, why don't we just say that theta is tangent inverse of b over a? And the answer to that question is that because it's not always true, right? If you think about tangent inverse, our discussion of the inverse trig functions, tangent inverse is going to map you to somewhere between negative 90 degrees and positive 90 degrees. You might be in quadrant 2 or you might be in quadrant 3, right? Or theta might be in quadrant 4, but it's got to be a positive angle. And so saying that theta is, for example, negative 30 degrees is no good, right? You'd have to say, well, you'd have to add 360 to that to say that theta is actually 300 degrees, right? Or what was it? I said negative 30, so theta would be actually positive 330 degrees, right? So theta does satisfy this equation, but then you have to make sure, first of all, that theta is positive, and that second of all, that you're in the right quadrant. In this case, 3, 1. So the moral of the story is that it's useful to draw a picture. And in this case, 3, 1, 1, 2, 3, 1, that's that vector right there. So obviously we're in quadrant 1. So in this case, taking tangent inverse is perfectly fine, right? It'll give us an angle in quadrant 1, which is exactly where we want to be. So let's see, what's tangent inverse of 1/3? So that comes out to about 18.4 degrees. Okay, and there's the direction angle. Okay, let's look at another example. So again, we want the magnitude and direction of this vector here, vector v. So magnitude is the square root of a squared plus b squared. Careful with your negatives. But this should be square root of 4 plus 4, which is square root of 8, or 2 root 2, if you simplify it. So there's our magnitude. The direction satisfies tangent theta is b over a. Okay, so tangent theta should be -1. And now here's where you're going to run into issues. If you take tangent inverse, you're going to get theta equals -45 degrees, which is not true because you need theta to be a positive angle. And we also need theta to be in the correct quadrant. So let's see what quadrant we're supposed to be in. 2, -2, so that would be that vector right there. So we need to be in quadrant 4. -45 degrees is in quadrant 4, but it's not a positive angle, right? We need theta to be a positive angle. So in other words, -45 degrees describes that angle right there. We want to be describing that angle right there. Okay. So, I mean, so the answer is going to be, it's going to be tangent inverse of -1. It's going to be tangent inverse of -1, but plus 360 degrees, so that you end up with a coterminal angle that's positive, right? Anyway, so 360 minus 45. So that's 315 degrees. Okay. Okay, so here's one more example. Now that you've seen a couple, I'll let you work on this one. See if you can get the magnitude and the direction angle. On the direction angle, just make sure that you're, first of all, in the correct quadrant, and second of all, that the angle is positive. But go ahead and give this a shot, right? Go ahead and pause the video, see if you can work this one out. Okay, sorry about that. I'm going to go ahead and work out my solution now. If I can get this thing pointed at a decent angle. Okay, here we go. So magnitude of W is going to be square root -3 squared plus 4 squared. That's the square root of 9 plus 16. Square root 25. Oh, hey, this one's pretty nice, right? Magnitude 5. Direction angle satisfies tan theta is B over A. So that's -4/3. Now, which quadrant do we need to be in? If W is -3, 4, so -3, 4, that would be that vector right there. So we're in quadrant 2. If I take tangent inverse of -4/3, I'm going to get an angle over here in quadrant 4. So what I need to do is add 180 degrees to it so that I end up here in quadrant 2 where I'm supposed to be. Okay, so in this case, we're going to say theta is tangent inverse of -4/3 plus 180. So let's see, tangent inverse -4/3 plus 180 is about 126.9. So I'll say it's about 126.9 degrees. Okay, and there's that one. So if you're trying to think, well, so to find theta, do I always add 180? Well, no. In the previous example, we added 360, right? And in the example before that, we didn't add anything. It was just tangent inverse, right? We didn't have to add anything. So the moral of the story is, don't try to find like a formula or something. Just think through it, right? Draw a picture, think through it, and make sure that you get theta so that you're in the correct quadrant. Okay, so that's that. Here's another example. Right, this one says vector u has magnitude 32.1 and direction angle 41.6. Rewrite vector u in the form AB. So rewrite it in its component form. To do that, you're going to use these two facts, right? The horizontal component is magnitude u cosine theta, and the vertical component is magnitude u sine theta. So I'll give you a second to work that one out, but it shouldn't be too terribly difficult. Okay, so here's my solution. So A is going to be magnitude u sine theta, cosine theta. So in this case, that's going to be the magnitude of u is 32.1. And the direction angle is 41.6 degrees. So it's 32.1 cosine 41.6. Okay, so that's about 24. And same way, well, similar with B anyway. So it's the magnitude of u times sine theta. So that's 32.1 sine 41.6 degrees. And that comes out to about, we'll say about 21. Oh, if we have three sig figs, maybe I should say 24.0 and 21.3. So there we go, right? So we would say u, so vector u equals a comma b. And that's all there is to that. So working with vectors algebraically is pretty nice. We can also add and multiply and stuff, just like we did geometrically. Only, again, I think it's a little bit easier algebraically than it is geometrically. But the addition stuff, it works just exactly the way you think it should, right? So if u is AB and v is CD, then u plus b is a plus c, comma, b plus d. So you just add components to components, right? If you're multiplying by a scalar, k, well, then you just distribute that to the components, right? So k times u is just ka, comma, kb. Same thing with a negative, right? You just distribute the negative. And same thing with subtraction, right? You just subtract components. So u minus v is going to be a minus c, comma, b minus d. So really no mysteries. It works exactly the way you think it should. So here's a picture. I'm not sure what picture exactly I was intending to draw here. I guess because we defined these things geometrically to begin with, when we're giving these algebraic rules, we should give some justification to show why they're the same as the geometric ones. So if I'm talking about u plus v, so maybe u is you know, here, and maybe v is there or something like that. And this would be the point AB. This would be the point CD. Right, u and v. But the thing is, I can take v and I can drag it up here, right? So that its initial point is there and its terminal point is, you know, up here or whatever. And if you're thinking about what this, what the resultant is, right? If you're thinking about what the resultant is, well, the x coordinate should be, it should be a plus c, right? And the y coordinate should be b plus d. So anyway, again, I think it's pretty straightforward, pretty intuitive. So here are a couple examples. I'll let you work these out. So if u is -2, 1 and v is 4, 3, see if you can find the following things and illustrate them. So I'll give you a second to work out part A. So go ahead and pause the video. I'm going to work out my solution now. So u plus v, first of all, is going to be -2 plus 4, comma 1 plus 3. Right? -2 plus 4 is 2, 1 plus 3 is 4. So that's not terrible. Oh, do I really need to draw this? I guess I will. So u is -2, 1. So it's this vector right here. And then we want to add 4, 3. For all intents and purposes, I can think of this like I'm starting at this point now. And 4, 3, I'm going to go 1, 1, 2, 3, 4, and then up 3. 1, 2, 3. Right, so that's V. And then this thing right here is U plus V. Right, so this is U plus V. And sure enough, right, 2, 4. Right, 2, 4. So geometrically, it works out the same as it would algebraically. I don't think I'm going to draw the rest of them. That's the idea. So -2u. Well, if u is -2, 1, then 2u should be, or the -2u should be 4, -2. Right? I'm just distributing the -2 here. So 4, -2. Okay, and that's that one. For part C, we have 3u minus 2v. So 3u is going to be 3 times -2, comma 3 times 1, minus 2 times v. That's going to be 2 times 4, comma 2 times 3. And then I need to subtract those. And again, I just subtract like components. Right? So -6 minus 8 is -14. And then 3 minus 6 is -3. And that's that one. Okay, so addition, subtraction, scalar multiplication. Those things are all fairly straightforward when you're working with the vectors algebraically. Another notation that we often use for vectors is we sometimes write vectors in terms of special unit vectors. And in this case, the unit vectors that we use are I and J. And these are like canonical vectors. It's like anywhere in math or physics you see an I like a bolded I or whatever, and a bolded J, then it's known that these stand for vectors 1, 0, and 0, 1, respectively. In 3 dimensions, I is the vector 1, 0, 0, J is the vector 0, 1, 0, and K is the vector 0, 0, 1, right? So, so you'll see these things if you ever take like physics. If you go on and take third semester calculus, you'll work with these things again. But anyway, for now, we're just going to use I and J, and we're just going to stick with 2 dimensions. But these things, we can rewrite any vector in terms of these 2 vectors. And I'll show you how in a second, but just a word notationally. As usual, these vectors can be expressed either in boldface or with arrows. However, sometimes they're written without any distinguishing features at all. So sometimes they're just written IJ, not bolded, no arrow over the top. And in fact, that's what I'm going to do in these notes because it's easier to type. But that's very common, is to not even have them bolded or with an arrow over the top. And then the other thing that's pretty common is that in physics, they're usually denoted with a little hat over the top. So I hat, J hat. In fact, sometimes they put the hat instead of the dot. So it would look like this in physics. Anyway, so all of these different notations, but at the end of the day, like when you see I, you know that it stands for vector 1, 0. And when you see J, it stands for vector 0, 1. It's a little unfortunate because in math, we already have a reason for using I, right? I is the complex unit. But anyway, but that's that. So as I said, any vector can be rewritten in terms of I and J. So to be specific, vector U, if vector U is AB, then another way to rewrite vector U is to say it's AI plus BJ. And here's a short little proof of that fact. So if we have vector AB, well, I can rewrite that as A0 plus 0B. And that should make sense, right? If you go backwards from this step to the previous step, then you would add the like components, right? A plus 0 is A, 0 plus B is B, right? And now I can factor out an A from the first vector, factor out a B from the second vector, and sure enough, this vector is just I, and this vector is just J, right? Anyway, but there's really nothing to it. I mean, that's the idea. So for example, we can rewrite the vector 2, -3 in IJ form as follows, right? Vector U is just going to be 2I minus 3J. And that's all there is to it. You'll have some opportunity to practice that in the homework. It's not terribly difficult. Okay. Now here's something new, and this is something that we can do when we're working with the vectors algebraically that we couldn't really do as easily geometrically, and it's that we can define the dot product. So I talked kind of briefly yesterday, or not yesterday, but in 7.4, I talked kind of briefly about the fact that you can multiply 2 vectors together in some sense. But we have to kind of define what that would mean. And here's the definition. So we call this thing the dot product. Okay, the dot product of 2 vectors, u and v, is denoted with a dot, right? U dot v. We read this vector u dot vector v, or just u dot v. And it's given by multiplying like components and then adding the results. So if u is AB and v is CD, then u dot v is AC plus BD, okay? A couple things to point out about this. So the dot product of 2 vectors is a scalar. notice that the result that you get here is just a real number. It's not a vector at all, right? So the dot product of two vectors is just a scalar, which is kind of interesting. Another thing that I want to say, going back to the two-dimensional versus three-dimensional thing, is that the vectors we're working with in this class are all going to be two-dimensional. But in third semester calculus and in physics, you would work with three-dimensional vectors often. And for three-dimensional vectors, there are two different kinds of products that we define. There's a dot product, which is defined similarly to the way we defined this one. But then there's also a cross product, which is, it involves matrices and determinants of matrices and stuff like that. It's really not terribly complicated, but I just don't want to get into it right now because you can't define a cross product for two-dimensional vectors. So cross products only exist for three-dimensional vectors. But the reason I wanted to bring this up is just to point out that, like, in grade school or whatever, when you're learning about multiplication, at first you learn this symbol, 6 times 2, and then later on you learn this symbol, 6.2, and when you're working with scalars, these are exactly the same thing. But when you're working with vectors, the cross product and the dot product are two very different things. So that's just something to be aware of when you move into calculus and or physics. Anyway, but for this class, we're only going to talk about the dot product, since the cross product is only defined for three-dimensional vectors, and we're only working with two-dimensional vectors here. So anyway, here are a couple examples. So for this first one, the dot product. So we want to do 2, 3, dot 4, negative 1. So we're going to multiply the components, right? So 2 times 4. This is going to be 2 times 4 plus 3 times negative 1. Oh, I said 2 times 4 and then I wrote the answer 8. Sorry, let me fix that. So it's 2 times 4. Sorry, so it's 2 times 4 plus 3 times negative 1. So that's 8 minus 3, which is 5. Okay, so there's that dot product. I'll let you work on part B, see if you can get part B on your own. Okay, so here's my solution for part B. So this is going to be negative 6 times negative 2 plus 4 times negative 3. Negative 6 times negative 2 is positive 12. 4 times negative 3 is negative 12. And we get 0. Okay, so 0. That's actually kind of a special thing, which we'll talk about in a second. But basically, what that means is that these two vectors are perpendicular to one another, or in other words, they're orthogonal to one another. And so we'll talk about that on the next page. But that's the idea. It should be pointed out that dot products could result in positive values or negative values or 0. If the dot product of two vectors is positive, then the angle between the vectors is acute. If the dot product of two vectors is negative, then the angle between the vectors is obtuse. And then if the dot product is 0, then the angle between the vectors is 90 degrees, right? The vectors are perpendicular. So to see why those things are the case, let's take a look at the next page. So now that we've discussed the dot product algebraically, here's the geometric interpretation, right? So if theta, so in some sense, as we commented on the previous page, the dot product is linked to the angle between two vectors, okay? So if theta is the angle between u and v, such that theta is between 0 and 180, then cosine theta satisfies this relationship. And we're going to prove this here down below. But just a comment before we do. So when I'm talking about theta has to be between 0 and 180, it's like, so imagine that you've got two vectors, maybe going off something like this. This forms two angles, right? It forms an angle this way, and it forms another angle this way. So the angle that we're interested in is the one that is less than or equal to 180. So in this case, this is theta, right? So that's the angle between the vectors that we're interested in. We're not interested in this one down here, right? Maybe we could call it alpha or something like that. But we're not interested in that angle. We're interested in theta. Okay. Anyway, so the angle between the two vectors satisfies this formula, right? U dot v, it's U dot v over magnitude U times magnitude v. And here's why. So let's draw a picture. Again, I'm going to draw this in quadrant 1, but it would work the same in any other quadrant that you drew this in. So let's say that U is down here or something, and that V is up here or something like that. So this is U. So the length of this vector down here is the magnitude of U. And the length of this vector is the magnitude of V. And this is the point A, B. This is the point C, D. And to derive this equation here, we're interested in looking at what this angle is between the two vectors. Well, in other words, we basically have like side angle side information. And so this sort of reminds us of a triangle. If we just complete this little triangle, and maybe we can call this M, we can call this length M, then applying the law of cosines, we would get M squared equals magnitude of U squared plus magnitude of V squared minus 2 times the magnitude of U times the magnitude of V times cosine of the angle theta. Right? So this just comes straight from applying the law of cosines to this picture. Well, so now if you think about what M should be, if you use the distance formula, you would say M is the square root of A minus C squared plus B minus D squared. Right? So M is the square root, therefore M squared is the square root squared, right? Which of course is just going to cancel off. You can do the same thing with U and V, right? Magnitude of U should be, it should be A squared plus B squared. Sorry, square root of A squared plus B squared. And magnitude of V should be square root of C squared plus D squared, right? The other magnitudes I'm not going to fill in because we want to preserve those in order to get the formula that we're looking for. So, but I'm not going to work out all the algebra here. It's not that complicated. You could, at this point, if you really wanted to convince yourself, it would be a good exercise to simplify this and combine like terms and sort of move everything over that you can. And if you were to do that, then you would end up at this point here where you see that A times C plus B times D is equal to magnitude of U times magnitude of V times cosine theta. A times C plus B times D. A times C plus B times D. Well, that's just U dot V, right? That's just the dot product of U and V. Okay, so A times C plus B times D just turns into U dot V. Okay. And then to get from here to the final step that we're trying to prove, well, you just divide through by magnitude of U times magnitude of V. And then sure enough, you see, right, cosine theta is U dot V over magnitude U times magnitude V. And that's all there is to that. Anyway, so there's the proof. Let's practice using that fact to find the angle between a couple of vectors. So, so let's find the angle between 3, 4, and 2, 1. Okay, well, we know that the angle is going to satisfy u dot v over magnitude u magnitude v. So I might start off by finding what all those things are, right? U dot v is going to be 3 times 2 plus 4 times 1. That's 6 plus 4, which is 10. Magnitude u is going to be square root of 3 squared plus 4 squared. We just did that a second ago. It's one of our favorites because it works out nicely, right? But that magnitude is 5. Magnitude v is going to be square root of 2 squared plus 1 squared. That's the square root of 4 plus 1, which is the square root of 5. And so now putting all that together, we know that cosine theta is going to be u dot v over magnitude u times magnitude v. Okay, that's 10 over 5 times the square root of 5. So that's 2 over root 5, or if you want to rationalize it, you could say it's 2 root 5 over 5. That's cosine theta. Of course, we want to find what theta is, so we'll take the inverse now. Now, here's the nice thing about this. So when we were finding the direction angle, we said, well, you can't just say that the direction angle is always tangent inverse, and that's true. But if you're trying to find the angle between the vectors, then it is true that theta is always cosine inverse of this stuff. Because if you think about cosine inverse is going to map you somewhere between 0 and 180, which is exactly where you want to be, right? So in this case, yeah, we can just safely take cosine inverse every time. So I'm going to say theta equals cosine inverse of 2 root 5 over 5. And I don't even need to draw a picture. I know for a fact that this is going to give me the angle I'm looking for. So cosine inverse of 2 root 5 over 5 is about 26.6 degrees. Okay. On the previous page, we said if the dot product of two vectors is a positive number, then theta is going to be acute. And we can see that here, right? The dot product was a positive number, and theta was acute. Okay, so that checks out. I'll let you work on part B. Okay, so go ahead and give the video a pause and see if you can work this one out on your own. Okay, here's my solution. So I'm going to do the same thing. I'm going to find the dot product. I'm going to find the magnitudes. And then I'll plug them into the formula. Sorry, so u dot v. 2 times 6 plus negative 6 times 2. Ah, well, I can already tell this is going to be 0. Magnitude u is 2 squared plus negative 6 squared. Not that it really matters. I mean, we don't really even have to do the rest of this because we know that we're going to get cosine theta equals 0. But just for the sake of argument, right, this would be square root 40, which is 2 root 10, if you simplify. Magnitude v is going to be exactly the same, I think, right? It's going to be square root of 6 squared plus 2 squared. So then we'd say cosine theta is u dot v over magnitude u magnitude v. That's 0 over 2 root 10 times 2 root 10. Who cares? It's just 0, right? It's just 0. So if cosine theta equals 0, then theta is cosine inverse of 0, which we know is 90 degrees. So sure enough, right? Like on the previous page, we said if the dot product of two vectors is 0, then the angle between the vectors is 90 degrees. Right? And that's true in general, right? That's true in general. So, so to make it even easier, right, we say if u dot v is 0, then u and v are perpendicular. Or another word for perpendicular is orthogonal. So you'll have a couple homework problems that ask you something like, determine which of these vectors are orthogonal. The easiest way to do that, what they're asking you is which of the vectors are perpendicular, right? Which of the vectors have a 90-degree angle between them, right? That's what they're asking you. And the easiest way to determine that is to find the dot product. If the dot product is 0, then the vectors are orthogonal. Otherwise, they're not. And that does it for this section.